Our next speakers are John Langton and Alex Baker from Bit9 Carbon Black, and they will be talking about visualization of large-scale security data. Thank you.
Hi, so Bit9 Carbon Black does endpoint security. We do prevention, detection, and response. And I'm in the R&D lab with Alex Baker under Chris Lord, and we do a lot of interesting things there, so it was kind of tough to come up with what exactly we were going to talk about today or narrow things down. We decided on visualization. So I'm specifically going to talk about scalability issues that come up with visualization when you're dealing with big data. We're going to give you some tips and tricks for scaling visualizations for big data, and we're going to talk about use cases specifically within the cybersecurity domain. So why visualization? What visualization is really about is leveraging human visual perception and processing. Humans are amazing at pattern recognition. In fact, we still beat computers at several tasks. So visualization is for a lot more than creating a pie graph to show your manager what you did last quarter. It can actually be used as part of the analysis process. Also, humans still have to make a decision. You're getting information from SIEMs, IPSs, IDSs, endpoint security. You have to make sense of all of this information and decide on an action to perform. Again, we're going to go through a few different use cases. Some real quick are basically monitoring, hunting, and of course, forensics analysis. So visualization, art or science, the first things that people often think of are either pie charts and bar graphs, or maybe you've seen a really fancy, complicated visualization at some point, but it didn't seem to serve any practical purpose. There's actually a lot of science behind visualization. There's decades of research where we basically project data mathematically into many different visual representations of that data. We sit users down at those displays, and then we give them a task. And this can be a cybersecurity task. You know, here's a PCAP, find what happened. And then we measure people's ability to find outliers, find patterns, answer the questions, find what happened. We can measure how fast they can complete the task. We can measure how accurate they're at completing the task. So as soon as you're able to measure something like that, you can start evaluating it. And that becomes a science. And there's also quite a lot of math in how you project from data into a visual representation. So here I just talk about a little bit about quantitative variables. So this is actual data. You can have categorical variables, and even within that, you can have ordinal and nominal variables. And there's also visual variables within visualization. And so after a lot of empirical studies, we've basically come up with ordered lists of which visual variables and visualization methods are best for portraying different types of data or for mapping. And so in the top, you have the quantitative, ordinal, and nominal, and basically which visual variables. Jock McInally came up with this one. Colin Ware has revised this, and several others have revised it since. So you can actually evaluate visualizations and how well they can perform. So as a simple example of what I'm talking about, why any of this matters, we can try a simple visual search task. So the task here is just to find the red circle. Here, the first slide is just using color, which is a pre-attentive visual processing cue for humans, so we can find it really quickly. Next slide, find the red circle. Might take a little bit longer, because you no longer have color as that visual cue. Next, find the red circle. Might take even a little bit longer. And so this is really just to illustrate how mapping data to different visual variables or using them, even things simple as shape or color, can really affect human performance and how quickly you can find patterns. And so here's the problem that we're facing with visualization. Basically, the pace and growth of data and processing is far outpacing the number of pixels that we have to display this information. So some of the classic problems are basically occlusion. So this visualization is called parallel coordinates, the visualization method. Each vertical line is basically a dimension of your data. In this case, we're showing a bunch of web traffic that's coming in. And a data point is essentially a line that cuts through each of the vertical lines. So here right away you get occlusion. You can obviously see it because you can't see the IP addresses. It's just sort of a black blur. But also it looks like there's more lines on the left side than there are on the right side. In actuality, it's the same number of lines because each line cuts a point through each vertical line. So all of the red lines are on the right side as well. They're just underneath the green lines. And so this shows a huge problem with occlusion, and this can even mislead forensics guys if they're, or gals as they're reading through logs and trying to find out what's going on. People often throw 3D out there. Oh, we can solve it with 3D. So 3D has the same occlusion issues. Basically, if you have enough data points, this will become a solid cube. Then you can only see the data points that are on the surface of the cube. You can't see the data points that are internal to that cube. Also, humans are not really great at depth cues. So we're not very accurate at reading information within a depth dimension. And of course, everyone's familiar with these sort of hairballs that you get at when you try to throw all of your data points into node link graphs. So I'm going to toss it over to Alex Baker. He's going to talk about some different methods for dealing with these issues.
Thanks, John.
So yeah, as John said, I'm going to just walk us through just a real quick overview of some techniques you can use to visualize your data when it gets big, when you get lots of rows, lots of columns, and also walk through some examples of ways John and I have used some of these techniques to visualize some large-scale cybersecurity data. So as John pointed out, in the simple case, you can take all your data points, you can lay them out X and Y, and you'll get all those patterns, but occlusion becomes a problem really fast. So one way to get around that is to say, rather than letting the data points place themselves, let's have some layout algorithms designed specifically to make sure that they all sidle up next to each other without anybody covering anybody else. So obviously, though, if you're going to set everybody side by side without overlapping them, you better make sure those things are small. You're going to run out of space really fast if your data is remotely large. You take that to its logical conclusion, you end up with something called pixelization. So here, each of these individual pixels here represents one specific underlying data point. And this is some of John's PhD research. This is a tool he built called IndieVis. And what it does is it takes an n-dimensional space and uses a technique called dimensional stacking to lay that out into a two-dimensional space in a way that preserves the patterns underneath. So this is 4 dimensions of data, 8, even better. 8 dimensions of data packed down to 2, and you can still see by the way it's laid out that you get these little patterns. You can still see these swoops on the big level. You can see off to the left in different dimensions, little patterns in these blue areas, and that all comes through because of the way the algorithm's designed. Now you might have a different problem. Maybe you don't have a whole bunch of dimensions. Maybe you just have one, but it's one that just goes on and on forever. You got data points from 1 to 1,000,000 to 1,000,000,000, and you're not just going to lay them out from left to right. You're going to run out of screen really fast. So what you want to do in that case is, one technique is this idea of Hilbert curves, which is a way to take a single long line, kink it up, put it in 2 dimensions, and what it does is it preserves locality. So if your key point of your data, where your pattern is from, say, data points 5,000 to 6,000, they're still going to form, at least loosely, some block in that 2-dimensional space, so that pattern will be preserved. So here's one example. This got around a little bit in 2012. It's a project called the Internet Census, and what they did is they used Hilbert curves, and they mapped the entire IP address space, considering it linearly, so from 0.0.0.0 to 255, 255, et cetera, laid it out in 2 dimensions using this Hilbert curves technique. And then what they did is they took 420 million data points about which of those IP addresses received or responded to ping requests. And so what you get is this kind of heat map of which regions of the IP address space are most active and which one of the ones are more dormant or at least not responding to requests. A technique John and I like for using IP addresses, showing large number of IP addresses, is actually use a hierarchical space-filling layout algorithm called tree maps. And what tree maps do is they take, as I said, hierarchical data and put them down into smaller subregions. So what we would do is we would take, for example, an IPv4 IP address, take the first octet and take everybody, OK, 192, you're going over here. 192.168 subregion. 192.168, and so on and so forth. So every subnet, as you get more specific, gives you a more detailed subregion within that visual space. And so there's a couple nice things about this. One thing is that it unlocks you from pixelization. You're no longer just locked into just having 1 pixel representing each of your data points. You can actually use that visual variable of size to depict interesting things. So you could have, in this case, we have, I think this is a bunch of IP addresses, and the size was the number of packets sent from that IP address that was being monitored. And the color was the number of particular alerts that were interesting. So the brighter the blue, the more alerts of that type. And so it lets certain regions, certain subnets pop out as of interest to us. We can say where the top talkers are. We can see regions kind of off to the right there, where we can say each of them individually isn't getting a lot of alerts, but everybody in that subnet has a little bit of action on this particular front. And so that's a region that we want to check out. And those patterns, because of the way that space is preserved, are allowed to pop out in the 2-dimensional projection. Now, as John was saying, you've got that graph. And as smart as you can possibly be about how you're laying all these things out, eventually you just got more data points than you've actually got pixel to display them. Even if you're getting big displays, you're just running out. It's not the kind of pacing it's going to keep up with. So if we're going to just go ahead and let them overlap, can we at least ameliorate the damage caused? Can we at least let it so that create a situation where even if they're overlapping, and now we're getting back that x and y coordinates, we're laying them out in x, y space, but we're not letting it be occlusion. We're not just saying, as on the left, every data point just knocks out the one behind it. We can use some transparencies so we let patterns emerge. So this is kind of a doctored data set here. But what it's done is it's a normal distribution in 2 dimensions with this ring pattern. And it's kind of a facile example, but what it shows you is that if you use that transparency, it allows the combined impact of particular points in that space to allow patterns to emerge visually. And this is basically the principle underneath the heat map. Again, this is something you might have seen. There's been a bunch of variations on this of people trying to show where the internet is in the world. And this is, again, the Internet Census Project. And they took, in this case, I think it was 460 million data points and laid them out instead of in the IP address space, in the global space in this case. And what they've done here is they're not actually necessarily drawing every IP address as a dot on there. They've got an algorithm that says, as points accumulate in a particular region or subregion, let's brighten that up and allow these hot spots and dead spots to kind of emerge. This is just kind of a more discrete notion of the same basic idea. You can take a scatter plot where you've got discrete values on the x and y axis, and rather than just saying data point 1 and 2 that fall in the same bucket obscure each other, you can say, let's let that bucket itself kind of accumulate individual data points. And we're going to change the color of that as more particular data points fall in that, so we can see regions that are hotter than others. So the downside of all this is that we're finding various ways around the large amount of data, but as a trade-off, we're losing all those cool visual variables. John had that big chart, and he'd said, at the top of all of them was position. So we've got position here, but if we're using those layout algorithms, we're no longer able to use the position of these particular data points to show where they're going. In this case, we've got position back. We can no longer use color or shape or size or any of those interesting things on the data points. So we've kind of beggared ourselves as far as how much we can say about the things that we're putting on screen. So the way you can kind of get out from under that is to use mathematical projections just to really say, I'm not going to actually take every data point and try to visualize it directly. I'm going to create smart aggregations that are going to represent a large number of underlying data points and visualize those. And so this is a real basic example. You're probably familiar with a scatter plot. It means each data point gets its own little nugget on screen. But for a bar chart, if you have 1 million rows of sales data, you're not going to make 1 million bars. You're going to do something where you're going to say, let's put those in some sort of aggregation. Let's say, all right, everybody who's in the first quarter, you go in this one. And we're going to do a sum across all those rows and make that the height. I mean, that's so intuitive, it probably seems like it's silly I'm even pointing it out. But that's the kind of thing that is underlying more advanced techniques where you're doing things in cybersecurity, for example. So we're looking at situations where if we've got network traffic and there's millions, billions of particular net flow data, PCAP data, alert data coming in. And even in situations if you're already just got an IDS and it's giving you alerts, we've talked to customers, they still have 250,000 alerts a day. So even if you have a system that's supposed to draw your attention to the interesting stuff, you've still got to find the interesting stuff inside the interesting stuff. And so if you can find ways to use visualizations to let those patterns pop out, you can do that with some smart aggregations. So for example, even if you've got different data types, as long as they've got something you can join on, for example, an IP address, you can say, all right, this node here is going to represent everything pertaining to this particular IP address. And we're going to use aggregations and choose the right ones that tell us what we want to know. So maybe we're going to say the size of the node represents the number of particular events that occurred with, or the number of packets sent by that IP address maybe. And maybe there's an alert that we're specifically interested in. Let's color it for that. And this can be arbitrarily complex. John and I were building a tool that you could take arbitrary SQL, other queries, and say, I want to know what the coefficient of variation over time of these kinds of alerts versus these other alerts is, and map that to the hue of that node. So it really opens up a lot of possibilities as long as you're choosing the right aggregations. You can really get the best of both worlds here if you start building into interlocking integrated views. So you can use this concept of providing a high-level overview. Here's your node link graph, and I kind of already snuck that in. We were already using aggregations by making each on-screen node represent an IP address, which might contain individual underlying data points. And you can say, I really want to know what's going on with that one. This is aggregated away on my individual data points. I want to find out what's going on under the hood. I might click on that individual node, and you can have an interconnected view that says on the top there, here's a timeline, and it's just going to filter. We're not going to show all the data points. There's too many, but we're going to show all the ones that pertain to that one you clicked. And now we're allowed to show you all kinds of other cool stuff about those individually. We can show, in this case, the start time, the duration, and you can color code them according to some particular type of that event. So you can say, orange shouldn't have been occurring there, whatever orange represents to you at this time. So I'm going to walk through a quick example of a tool John and I built for visualizing cybersecurity data that uses a series of interlocking views and that uses several of the techniques I've talked about. So again, in the bottom right, we've got our tree map. And again, that's showing it according to those IP address octets hierarchically. And size is number of packets, red is number of alerts. What we've also got is in the top left a visualization, the same IP address space, same IP addresses, except in this time, instead of organizing them according to the location of the network, we're doing it according to their active connections between particular IP addresses. The important thing to do is to make sure you interlink these. So if you've got two different visualizations that are using the same abstraction, when I click on a node in one of them, I want to know where the corresponding node is in the other one. So I can say, not only is this guy big and red and that's bad, but look who he's talking to. And those things together are really going to maybe draw my attention to that particular interaction, that particular space in the data. Taking that a step further, you could then do this kind of drill down where you've got this timeline graph in the bottom left here. And this is itself actually pretty space efficient. Each of those little individual squares in there represents an individual event. In this case, it's packet capture data. Individual packets sent by this particular IP address. And it lays them out in a way such that it's across time, creates these little buckets where they stack up. So you get this histogram of overall activity, but also respect the individual elements. So you might say, wow, at this spot, that's a weird spike. That's the spot that seems to caused my interest to in drawing these IP addresses in the first place. You can drag your mouse across that, and we have some brushing where that'll then drag this even further into actual underlying details. So you've got this table in the top right here, and these rows represent the colored pixels in this bottom left area. And so you might decide at the very bottom of this, like there, that's the event, that's the one I was looking for, that's the problem, and this isn't the end of my investigation though. What I can then do is I can say, click on that element and say, where else did this happen in this timeline? And furthermore, are there any other IP addresses that showed, according to whatever similarity heuristic you've described, have similar behavior going on? So you can really work your way through this. And again, it's taking the best of both worlds as far as all the computer's ability to lay all these things out and handle all that underlying data and run these queries, but the human's ability to notice patterns that are hard to describe algorithmically as far as like, that looks weird, that looks different. Let me go ahead and dig through this with my own intuition about how things ought to look and where I want to look next. So you don't have to go necessarily this far with this, but I think there's a variety of ways that you can take your large amounts of data, and even if you're not building a giant interconnected framework, even just putting together a smart visualization of your data points, whether as a space filling visualization or using occlusion or avoiding occlusion in smart ways. I think there's a lot of ways you can get at insight of these, and I would wager that honestly some of the problems that we saw, some of the threats that we saw earlier in the talks, would have probably popped out much more quickly, would have been detected much more quickly if they'd had even a simple visualization that was checked once a day. So just throwing out a few ways that we can start to look at this, and I'm going to throw it back to John.
It's not over yet. Thanks. Sorry, we're confusing you with the pass-offs. Just want to talk about some engineering issues real quick. We've only got 20 minutes, so we can't dive into details on any of this stuff. But basically, anything that you can buy off the shelf right now is going to load everything into working memory. So your BI tools, all the typical things. So if you're really dealing with data at scale, you're going to have to home cook this stuff. And my advice for doing that is to leverage your data store for projection and modeling. So there's a lot of different mathematical functions for doing the aggregations, many different options for aggregation functions that you can do. Do that all in the data store. Don't load everything in the memory and then do it, because that's what your BI tools and things are doing. And so those are not going to scale. And also just wanted to give a quick shout out if you're dealing with too many dimensions. There's traditional methods for dealing with that: principal components analysis, multidimensional scaling. But also dimensional stacking is a visualization method. There are also visualization methods that just lend themselves well to lots of dimensions. And some of the stuff that we're doing right now, so we're doing a lot of really cool machine learning projects at Bit9. And so I just want to talk about how we're using visualization. So in the upper left here, we basically have every field. We're looking at basically binaries. And we're taking a lot of different features out of those binaries, and we're plotting every feature by every other feature. And what we do is we can take a lot of different metrics on that: mutual information, correlation, different statistical analysis, and then map that into color gradients. And that can give us a real bird's eye view. So even if you didn't understand all that stuff, basically just look at what is the brightest green thing, right? So those are the fields that are basically saying the same information. And so we might want to basically not use all of those in our machine learning algorithms, select only one. So we can get a really quick bird's eye view of what's going on and decide on our inputs. So it's great for feature selection. Also, we can look at independent features, see if they're great at separating data, nonlinear and linear dependencies between malware and goodware. We went ahead and did some clusterings ourselves too. We saw some cool visualizations earlier of clustering. So we also, clustering is really great if you have unlabeled data, if you don't have those classes, if you don't know what those families are, because clustering can be used to basically use machine learning to figure out emergent classes. And so here we get like these nice little beautiful clusters popped out based on different features. In this case, we're looking at imports and basically how does malware relate to each other. And so each little grouping here can be different families of malware. And then we can use that to inform us further of different inputs to use into our machine learning algorithms later. So these are real use cases of where visualization is really helping And just to briefly go over what we talked about using layout, so this is tips and techniques for visualization at scale, using different visual variables, doing projection aggregations in the database, coordinated views, and also interaction. If you want to try this yourself, there's a lot of sources of information out there. I have to warn you that most of them are wrong. They're very wrong. So be careful about what you look at. And visualization is one of those areas where people just want to dive in, and everyone has a really strong opinion. But we do recommend Data-Driven Security blog. There's also a book by Jay Jacobs and Bob Rudis. Sort of the textbook right now for visualization is Interactive Data Visualization by Matt Ward, Joseph Gridstein, and Daniel Keim. And you can always check out our old blog with use cases in cybersecurity. Thanks very much.